There's a number that few drivers know, but it can completely change how they see a car. 7.9%. This is the lowest rollover probability rate ever recorded by the National Highway Traffic Safety Administration for an SUV, and it belongs to the Tesla Model Y, which will hit the market in the second half of 2026. Behind this seemingly simple number lies an engineering story that most people have never stopped to consider. Every time a driver nearly lost control on a sharp turn, every time a crosswind tried to push the car out of its lane, something invisible held the vehicle in place before anything happened. And that something is hidden right under the driver's feet. Imagine a common situation on American highways like I-10. A driver is traveling at about 110 kilometers per hour when out of nowhere, a pickup truck veers into their lane without signaling. Instinct dictates a sharp turn of the steering wheel, and at that instant the car needs to respond exactly as the brain dictates, without hesitation, without extra swaying, without that feeling that the vehicle will continue moving after the maneuver is complete. It is precisely in this type of scenario that the battery design of the 2026 Model Y shows its worth. Tesla didn't treat the battery pack as just a power source, but as a tool capable of shaping the physical behavior of the entire car. In the new Model Y, the American brand has transformed the entire floor of the vehicle into a single flat battery pack that extends from the front axle to the rear axle like a kind of chessboard. This assembly weighs between 450 and 545 kilograms, depending on the version, and represents the heaviest part of the entire car. Instead of concentrating this weight at a single point, music as happens in combustion engine vehicles where the engine is tucked under the hood, the engineering has spread this mass evenly across the entire base of the car, a few centimeters above the ground. The effect of this is difficult to perceive at a quick glance, but becomes evident as soon as the car starts moving. Tests conducted by the National Highway Traffic Safety Administration are considered one of the most rigorous benchmarks in the world when it comes to vehicle safety. And the result obtained by the 2026 Model Y has caught the attention of the automotive industry as a whole. The 7.9% rollover probability rate is considered extremely low for any vehicle in the SUV category, especially when compared to traditional models that usually present numbers between 15% and 25%. This percentage represents the statistical chance of the car rolling over during a high-speed emergency maneuver, such as a sudden swerve to avoid an obstacle on the road. The lower the number, the greater the probability that the vehicle will remain with all four wheels on the ground even in extreme situations. To understand why this number is so significant, it's necessary to consider how a rollover actually happens. When a driver makes a sudden swerve at high speed, the car's mass tends to continue moving in its original direction, creating a lateral force that pushes the upper part of the vehicle outward from the curve. In conventional SUVs, this force encounters a relatively high center of gravity, which increases the leverage effect and can cause the car to tilt to the point of tipping over. In the Model Y, this same lateral force encounters resistance precisely because the weight is concentrated in the lowest possible part, close to the asphalt. The result is that the vehicle simply cannot perform the tilting motion that causes a rollover. The even weight distribution across the wheelbase also plays a decisive role in this behavior. Because the battery pack extends from the front to the rear axle, stability isn't concentrated in just one area of the car, but manifests itself symmetrically across its entire length. This means that both music, the front and rear, respond similarly to external stimuli, without the imbalance common in vehicles with poorly distributed weight. In real-world conditions, this translates into a feeling of predictability. The driver intuitively understands how the car will react before even taking any action, which significantly reduces the chance of desperate maneuvers that could lead to loss of control. Another scenario where this engineering proves particularly effective is when the vehicle faces crosswinds on open highways. Anyone who has ever driven on flat roads with crosswinds knows the uncomfortable feeling of having the car pushed sideways, requiring constant steering corrections to maintain trajectory. In tall SUVs with poorly distributed weight, this effect is amplified because the side area of the vehicle acts like a sail, catching the wind while the upper part of the body sways in response. The precise location of the battery pack between the front and rear axles was an engineering decision that goes far beyond simply fitting parts into the available space. Tesla positioned all the vehicle's heavy mass precisely in the middle of the car, creating a weight distribution close to 50% for each axle. This type of balance is usually associated with high-performance sports cars such as BMW M or Porsche models, where engineers strive to achieve this proportion using complex motor and transmission positioning techniques. In the case of the Model Y, this balance arises naturally precisely because the battery, being the heaviest component, occupies a perfectly central position underneath the vehicle. This arrangement produces a dynamic behavior rarely found in cars powered by combustion engines. Traditional vehicles tend to be heavy in the front since the engine is positioned under the hood, while hybrid models face the challenge of balancing two different propulsion systems, often resulting in uneven weight distribution. Tesla solved this equation by placing most of the mass not only low, but also centrally, which fundamentally changes how the car reacts when the steering wheel is turned. In practical terms, the vehicle ceases to behave like a typical SUV and begins to exhibit responses reminiscent of much more agile and sporty cars. This behavior can be seen more clearly in what experienced drivers often call second movement. Imagine someone driving at 110 km per hour on a highway and needing to overtake a truck. The person turns the steering wheel to change lanes. The car moves, and in many vehicles the body continues to oscillate slightly after the maneuver should have already ended. This floating sensation is the result of the car needing a second correction to fully stabilize. In the Model Y, because most of the mass is centralized and low, the forces are distributed more evenly and the body settles almost instantly after the driver's first command. In other words, the driver turns the steering wheel once, the car responds once, and the movement simply ends there. There's no sense of continuity, nor the need to make small complementary adjustments to keep the vehicle in the intended lane. This may seem like a small detail in a written description, but it represents a huge difference in real-life situations, especially in emergency maneuvers. When an unexpected situation occurs on the road, such as an animal crossing or a tire blowout on another vehicle, the driver's reaction time is crucial. Having a car that executes exactly what was asked on the first attempt can be the difference between avoiding an accident and being involved in one. In the latest versions of the Model Y equipped with 4,680 cells, Tesla's engineering has taken a step far beyond what virtually any traditional manufacturer had done before. The battery has ceased to be just a component placed inside the vehicle and has become an integral part of the car's structure itself, literally functioning as the floor. This means that the seats, panels, and other body elements are fixed directly onto the battery pack without the need for a separate intermediate structure to support them. Instead of building a body and then fitting the battery inside it, Tesla is building a body where the battery is the base itself. To understand how this works in practice, it's helpful to imagine a sandwich-type structure. The battery cells are bonded between an upper layer and a lower layer, both made of strong and lightweight materials. This entire assembly forms a single solid piece, combining the function of storing energy with the function of supporting the vehicle's weight. When the car goes around a curve or receives a side impact, the battery cells themselves participate in distributing the forces, behaving similarly to structural walls in a building. Instead of just storing electricity, they actively work to keep the car rigid and stable. The result of this approach is a significant increase in torsional rigidity, which is the chassis' ability to resist twisting when subjected to lateral forces. This aspect rarely appears in marketing brochures or superficial comparisons between vehicles, but it represents one of the most important factors in the driving quality of any car. A stiffer chassis means that the car does not deform minimally when the driver turns the steering wheel. And this microscopic difference produces enormous consequences in the driving feel. Every movement of the tires against the asphalt is transmitted almost instantaneously to the body and, consequently, to the hands of the driver. In real-world driving situations, especially on winding roads like the Angeles Crest Highway in California, or when you need to quickly swerve to avoid an obstacle, this characteristic becomes evident. In cars with more flexible chassis, there is always a slight delay between the moment the driver moves the steering wheel and the moment the body actually follows that movement. This delay can be only fractions of a second, but the human brain perceives this difference and interprets it as a lack of precision. In the Model Y with its integrated structure, the steering wheel and body seem to move in perfect synchronicity, creating a feeling of direct connection between the driver and the road. When a car's chassis has high torsional rigidity, the most immediate effect the driver feels is a virtually instantaneous response between steering input and the vehicle's reaction. In the Model Y, this characteristic reaches a level rarely seen in conventional SUVs, precisely because the integration of the battery as a structural element eliminates bending points that would normally exist between the input and output points. Each steering wheel movement translates into an equivalent movement in the wheels without the intermediate hesitation that many drivers associate with soft or uncomfortable cars. Steering becomes a natural extension of the driver's intention. To illustrate this difference in practice, it's worth comparing what happens in active driving situations such as a mountain road full of consecutive curves. In a vehicle with a more flexible chassis, the driver turns the steering wheel and notices that the body takes a fraction of a second to follow the movement, creating a feeling of disarray. This small delay forces the driver to anticipate their actions, turning the steering wheel slightly earlier than necessary to compensate for the structural flex. In the Model Y, this anticipation becomes unnecessary, since the steering wheel and the body move practically in sync. The result is cleaner, more precise, and less tiring driving on demanding stretches. This precision is also particularly useful in emergency situations when fractions of a second make all the difference between avoiding an accident and being involved in one. Imagine a scenario where a pickup truck veers into the driver's lane without warning, requiring an immediate swerve. In a car with a less immediate response, the time between turning the steering wheel and the vehicle actually changing trajectory can be enough to render the maneuver ineffective. In the Model Y, this gap practically disappears and the car moves laterally almost instantly upon receiving the command. This difference, which seems theoretical in a written description, can be decisive in critical moments in traffic. Another interesting aspect of this engineering is the fact that Tesla managed to achieve these gains in rigidity without adding extra weight to the vehicle. In traditional designs, improving torsional rigidity usually requires additional metal reinforcements, structural bars, and thicker materials, all elements that increase the total mass of the car and impair energy efficiency. The American automaker solved this equation differently, taking advantage of something that was already present in the car for other reasons, namely the weight of the battery itself. Instead of treating this mass as an obstacle to be compensated for, the engineers transformed it into a structural advantage, improving drivability without compromising other aspects of the design. Every engineering choice carries a series of consequences, and the 2026 Model Y is no different. Despite significant gains in stability and precision, the all-wheel drive version weighs approximately 2,030 kilograms, a considerable number for a vehicle in this category. To manage this mass effectively, Tesla had to adopt a firmer suspension calibration than the market average, which has a direct effect on interior comfort. On perfectly smooth surfaces, this goes practically unnoticed, but on streets with expansion joints, aged asphalt, or concrete pavements, the sensation changes considerably. Many owners report that the car transmits vibrations and impacts more clearly than traditional SUVs, especially on urban stretches with uneven pavement. This characteristic is a direct consequence of the decision to prioritize stability over impact absorption. A softer suspension would certainly make everyday driving more comfortable, but it would also allow more body roll in curves and lane changes, compromising precisely the qualities that make the vehicle so stable at music high speeds. The manufacturer chose to preserve dynamic behavior in critical situations, even if it means sacrificing some smoothness in everyday situations. There is also a more subtle issue related to the car's behavior at the limits of grip. When engineering concentrates a large amount of mass in the center of the vehicle and keeps the body firm, the car tends to remain composed and flat for longer during an aggressive turn. In traditional SUVs, the progressive body roll acts as a visual and sensory warning that the driver is approaching the vehicle's physical limits. In the Model Y, this warning is less pronounced, precisely because the car maintains a nearly flat stance until the very last moment. When the forces finally exceed what the tires can withstand, the transition can happen more abruptly than expected. This behavior can lead less experienced drivers to overestimate the car's actual cornering capabilities, especially on unfamiliar roads or in adverse conditions. The feeling of stability generates confidence, but that same confidence can turn into surprise when the limit is finally reached. Another point that deserves attention involves the costs associated with maintaining the integrated battery architecture. When the cell pack becomes a structural part of the car, any failure in an individual component can require complex interventions. There are records of owners facing repairs that reached approximately $16,000 for relatively minor problems in the system, precisely because partial replacement is not always technically feasible. When comparing Tesla's approach to that of other traditional automakers, the difference lies not only in technical details, but also in completely distinct design philosophies. Ford, for example, adopted a similar strategy in the Mustang Mach-E, positioning the battery in the vehicle's floor to lower the center of gravity and improve axle balance. However, the American brand still treats the battery pack as a separate component installed within a pre-built structure, rather than integrating it as part of the body itself. This type of approach produces positive results in terms of stability, but owner reports still mention some noticeable body movement on uneven surfaces. Toyota, on the other hand, chose an even more conservative approach with the BZ4X. The Japanese automaker prioritized comfort by maintaining a taller body, approximately 1.65 m in total height and about 21 centimeters of ground clearance. This type of configuration provides a smoother feel on bumpy roads and gives the driver a higher driving position, a characteristic that many consumers associate with the traditional SUV experience. The downside of this design is a higher center of gravity and a less immediate response in abrupt maneuvers, with the body exhibiting more body roll in curves and rapid changes of direction. Tesla opted for a direction opposite to these two strategies. The 2026 Model Y maintains a total height of approximately 1.62 m and only 17 centimeters of ground clearance, deliberately sitting closer to the asphalt than its main competitors. This decision sacrifices some off-road capability and reduces the elevated driving position that many buyers seek in an SUV, but in return offers dynamic handling that is much closer to that of a traditional sports car. In simple terms, while Ford seeks a balance between worlds and Toyota prioritizes comfort, Tesla aggressively bets on physical stability as the vehicle's main characteristic. This philosophical difference also appears in how each automaker handles behavior management systems. Traditional brands often rely on sophisticated suspension tuning, electronic stability control systems, and software calibrations to compensate for the physical, music limitations inherent in their vehicle's design. Tesla also utilizes these electronic resources, but builds stability first at the physical level of the car, transforming the battery's own weight into a structural ally before any electronic system even needs to intervene. This creates an additional layer of predictability, since the vehicle's basic behavior doesn't depend exclusively on algorithms to function properly.